Every single second, roughly 10,000 photons of ancient light strike every square centimeter of your skin. You cannot feel them. You cannot see them. But they are there, washing over you right now, a faint cosmic rain that has been falling since long before the Earth existed. These photons were born roughly 380,000 years after the beginning of everything. When the universe finally cooled enough for atoms to form and light to travel freely for the first time, they have been sailing through the void ever since, across 13.4 billion years of space, carrying in their wavelengths a kind of baby photograph of the entire cosmos. They are the oldest light in existence, and you are bathed in it right now. The fact that we know this, that we can say with confidence that the universe is 13.8 billion years old, is arguably the most extraordinary intellectual achievement our species has ever pulled off. Think about it. A collection of evolved primates clinging to a small rocky planet, orbiting an utterly ordinary yellow star, tucked into a quiet arm of one galaxy among trillions. Somehow figured out when everything began, not approximately, not within a few billion years. We know the age of the cosmos to within about 20 million years. That is a margin of error of roughly 0.1%. For context, that is like guessing someone's age to within a single hour over the span of an entire human lifetime. But this knowledge did not come easily. It did not arrive in a flash of divine insight or a single eureka moment. It came slowly, painfully, across thousands of years of wrong answers, bitter arguments, missed clues, and lucky accidents. It is a story that stretches from the ziggurats of ancient Babylon to the frozen detectors of a European space telescope orbiting 1,000,000 miles from Earth. It involves priests and poets, farmers' daughters and Nobel laureates, a pair of confused engineers trying to scrape pigeon droppings off an antenna in New Jersey, and a man who escaped the Soviet Union by kayaking across the Black Sea. This is the story of how we learned the age of the universe. And it begins, as all such stories must, with people staring at the sky and wondering. For tens of thousands of years, human beings have looked upward at the night and asked, how old is all of this? When did it begin? Has it always been here? And every civilization that ever raised its eyes to the stars constructed its own answer. In ancient Mesopotamia, the Babylonians imagined a cosmos born from primordial chaos. Their creation epic, the Enuma Elish, dating back roughly 3,000 years, describes the god Marduk slaying the sea goddess Tiamat and fashioning the heavens and the earth from her dismembered body. In this view, the universe was not inconceivably old. It was a crafted thing, assembled by divine hands in a time that felt almost reachable. Their cosmos was layered, a three-tiered structure of heavens, earths, and underworlds, 6 planes of existence stacked atop one another, with the stars inscribed like cuneiform writing into the lowest heaven. It was intimate, it was personal, and it was fundamentally wrong about almost everything. But it was a start. The ancient Egyptians saw things differently. Their cosmos revolved around the sun god Ra, who was born from the sky goddess Nut each dawn, traveling across her star-speckled body before being swallowed each night in an eternal cycle of death and rebirth. For the Egyptians, the universe was self-creating and endless. Time was circular, not linear. The cosmos did not age because it had always been and would always be. There was no first moment. There could be no last. Across the world, the Hindu tradition arrived at something remarkably different and, in a certain way, remarkably prescient. Hindu cosmology envisions time on a scale that would not look out of place in a modern astrophysics textbook. A single day of Brahma, the creator god, spans 4.32 billion years. A full day and night cycle doubles that to 8.64 billion years, and Brahma's own lifespan encompasses cycles upon cycles, a universe that breathes in and out, expanding and contracting, being born and dying, and being born again across timescales that dwarf anything the Western world would conceive for millennia. Carl Sagan, the great astronomer and science communicator, once noted that Hinduism is the only major world religion in which the cosmic timescales correspond, at least roughly, to those of modern cosmology, whether by some extraordinary coincidence or by a deep philosophical intuition about the nature of things. Ancient Indian thinkers were reaching toward a truth that would take the rest of the world thousands of years to grasp. The ancient Greeks brought something new entirely. Beginning around the 6th century before the Common Era, thinkers like Thales, Anaximander, and later Aristotle began to strip away the mythology and ask a different kind of question, not which god made the universe, but what is the universe made of and how does it work? Aristotle proposed a cosmos divided into two realms: the terrestrial, a place of change and decay composed of earth, water, air, and fire, and the celestial, a perfect and unchanging domain governed by a mysterious fifth element he called the quintessence. In Aristotle's view, the heavens were eternal. They had always existed. They would always exist. Change was confined to the messy, imperfect world below the orbit of the moon. The stars and planets were immutable, embedded in crystal spheres that turned with divine perfection. This idea of an eternal, unchanging cosmos proved remarkably durable. It would outlast the civilization that birthed it by many centuries. When the Roman Empire absorbed Greek learning, the Aristotelian cosmos came with it, and when Rome fell, the torch passed eastward. During the Islamic Golden Age, stretching roughly from the 8th through the 13th centuries, scholars like al-Biruni, al-Battani, and Ibn al-Haytham preserved, translated, and refined Greek astronomical knowledge. Al-Biruni, writing in the 11th century, calculated the circumference of the Earth with remarkable accuracy. Al-Battani improved the measurement of the solar year to within 2 minutes of the modern value. But these brilliant astronomers largely operated within the inherited framework. The cosmos was either eternal, or it was created by God at a single moment in the past. The question of when was a theological matter, not a scientific one. In medieval Christian Europe, the Greek cosmos was baptized into the faith. Thomas Aquinas, the towering 13th century theologian, married Aristotelian physics to Catholic doctrine, creating a vision of the universe in which the celestial spheres reflected God's perfection. The age of the universe, in this tradition, was derived not from observation, but from scripture. Bishop James Ussher, the Archbishop of Armagh, in the 17th century, famously calculated from biblical genealogies that creation had occurred on the evening preceding October 23rd, 4,004 years before the birth of Christ. The universe, in Ussher's reckoning, was roughly 6,000 years old. It was a precise number, confidently stated, and wrong by a factor of more than 2 million. The great upheavals of the scientific revolution dislodged many old certainties, but the question of cosmic age proved stubbornly resistant. Copernicus moved the sun to the center of the solar system. Kepler showed that planets move in ellipses. Galileo pointed his telescope skyward and found mountains on the moon, spots on the sun, and moons orbiting Jupiter. Each discovery cracked another piece of the Aristotelian edifice. But none of them answered the fundamental question: how old is all of this? Even Isaac Newton, whose laws of gravity and motion revolutionized physics in the late 17th century and gave humanity its first truly predictive mathematical framework for understanding the heavens, assumed an infinite, unchanging universe. Newton's cosmos was a vast, static void in which stars hung like grains of sand, scattered through an endless darkness, stretching outward in every direction forever. He recognized a fundamental problem with this picture. Gravity is always attractive, so the mutual gravitational pull of all the matter in the universe should, over time, cause everything to collapse into a single enormous clump at the center. But Newton believed he had a solution. He argued that if the universe was truly infinite, extending forever in every direction, then the gravitational pull from one side would be perfectly balanced by the pull from the other. Every star would be tugged equally in all directions, and the net force would be zero. The universe could stand still. It was a clever argument, elegant in its simplicity. It was also deeply flawed. In the 19th century, mathematicians would show that Newton's argument about infinite gravitational balance does not actually work, that an infinite uniform distribution of matter under gravity is fundamentally unstable. But this instability would not be fully appreciated until Einstein's general relativity provided a new framework. For 2 centuries, Newton's static, infinite cosmos remained the default assumption of Western science. The first serious cracks in the idea of an ageless cosmos came not from the stars above, but from the rocks below. And the story of how humanity first learned the age of the ground beneath its feet is itself a tale of fierce argument, wounded egos, and a revolution sparked by a force of nature that nobody could see. In the late 18th century, the Scottish geologist James Hutton began examining the layered strata of the Scottish coastline. The bands of sandstone and limestone and shale that had been laid down over unimaginable spans of time, then lifted, folded, eroded, and laid down again, looking at the deep, winding unconformities where ancient eroded surfaces were buried beneath newer deposits. Hutton concluded that the Earth showed, in his famous phrase, no vestige of a beginning, no prospect of an end. The planet was old, far older than anyone had dared imagine. His younger colleague Charles Lyell pushed this idea further, arguing in his influential 1830 work, Principles of Geology, that the same slow processes operating today, erosion, sedimentation, and volcanic activity, had always operated at roughly the same pace. If that were true, the Earth had to be staggeringly ancient to account for the landscapes that surrounded them. But how ancient? On that point, the geologists could only wave their hands. They had no clock. Enter Lord Kelvin, or more precisely, William Thomson, who would become Lord Kelvin in 1892, one of the most towering figures of 19th century physics. Kelvin was a man of formidable intellect and equally formidable confidence. He had helped lay the first transatlantic telegraph cable. He had formulated the second law of thermodynamics. He had done more to advance the science of heat than perhaps any person alive. And in 1862, he turned his considerable mind to a question that seemed perfectly suited to his expertise. How old is the Earth? Kelvin's reasoning was elegant and on its own terms, seemingly airtight. He knew that the deeper you dig into the Earth's crust, the hotter it gets. Miners had known this for centuries. The deepest shafts of European coal mines were sweltering, sometimes dangerously so. This geothermal gradient, a temperature increase of roughly 1 degree Fahrenheit for every 50 feet of depth, meant that heat was flowing continuously outward from the Earth's interior to its surface, radiating away into space. If the Earth had once been a molten ball of rock, as most scientists believed, an assumption supported by the existence of volcanoes, hot springs, and the increasing temperature of deep mines, then the rate of this heat loss could be used as a cosmic clock, using the elegant mathematics of Fourier's heat conduction theory, which Kelvin had studied as a teenager and mastered as a young man, and applying the known thermal properties of rock and an assumed initial temperature of around 7,000 degrees Fahrenheit, Kelvin arrived at his answer. The Earth was somewhere between 20 million and 400 million years old. He later narrowed this to about 20 to 40 million years, and he stated his conclusion with the absolute confidence of a man who trusted mathematics above all else. The geologists were horrified. 20 million years was nowhere near enough time to account for the vast strata of rock they studied. Charles Darwin, whose theory of evolution by natural selection required enormous stretches of time for the slow accumulation of tiny changes, was particularly distressed. He called Kelvin an odious specter and listed the physicist's age constraints among his source troubles. Darwin's champion, Thomas Huxley, fired back in an 1869 lecture, arguing that Kelvin's calculations appeared precise, but were built on dubious assumptions. But Kelvin held firm. He was the most famous scientist in Britain, and nobody could find a flaw in his mathematics. Nobody could, because there was no flaw in his mathematics. The flaw was in his physics. Kelvin had assumed that the Earth's only source of internal heat was the residual warmth from its formation. He did not know, and could not have known, about a phenomenon that had not yet been discovered: radioactivity. In 1896, the French physicist Henri Becquerel stumbled onto something strange. A photographic plate left near a sample of uranium had been exposed, as if by light, even though it had been kept in the dark. Within 2 years, Marie and Pierre Curie had isolated 2 new radioactive elements, polonium and radium. And in 1903, Pierre Curie and Albert Laborde made a remarkable announcement. Radium produces enough heat to melt its own weight in ice in less than an hour. The implications hit geologists like a thunderbolt. If radioactive elements within the Earth were continuously generating heat, then Kelvin's entire calculation was invalidated. The Earth was not simply cooling from an initial hot state. It had an internal furnace that had been burning for billions of years. The physicist Ernest Rutherford grasped the significance immediately. In 1904, he gave a lecture at the Royal Institution in London on the new science of radioactive dating. As Rutherford himself later recalled, he entered the half-dark room and spotted Lord Kelvin in the audience, and realized he was in trouble when he came to the part of his talk where his views directly contradicted Kelvin's. To his relief, the old physicist fell asleep. But as Rutherford reached the critical point, Kelvin sat up, opened an eye, and fixed him with what Rutherford described as a baleful glance. Then, in a flash of inspiration, Rutherford said that Lord Kelvin had limited the age of the Earth, provided no new source of energy was discovered, and that this prophetic utterance referred to what they were now considering that night: radium. At this, Kelvin beamed with apparent approval. though he never publicly retracted his own estimates, going to his grave in 1907 still skeptical of radioactivity's importance. But Rutherford was right, and the new science of radiometric dating transformed the question of Earth's age from philosophical speculation into measurable fact. Rutherford suggested that trapped helium from radioactive decay could serve as a geological clock. His colleague Bertram Boltwood refined the approach, tracing the decay of uranium through a series of steps down to its final stable product, lead. By measuring the ratio of lead to uranium in a rock, you could calculate how long that rock had existed. Boltwood's early estimates, published in 1907, pushed the age of certain rocks back to over 2 billion years, demolishing Kelvin's limit at a stroke. Arthur Holmes, a young British geologist and a student of Robert Strutt, became the great champion of radiometric dating when nearly everyone else had given up on it. In 1911, Holmes measured the age of rocks from Ceylon, now Sri Lanka, at about 1.6 billion years. He published these results in his landmark 1913 book, The Age of the Earth. The estimates were rough, but they were pointing unmistakably in one direction. The Earth was billions of years old, not millions. The definitive answer would come from an unlikely source. In the 1940s, a young American geochemist named Claire Cameron Patterson was working on the Manhattan Project at the University of Chicago, where he had been drafted into the wartime effort to develop atomic weapons. Born on a farm in Mitchellville, Iowa, in 1922, Patterson was unassuming, meticulous, and stubborn in the best possible way. During the war, he developed extraordinary skill with mass spectrometers, the precision instruments used to separate and measure the exact masses and abundances of individual isotopes of elements. These instruments, crucial for the Manhattan Project's uranium enrichment program, would become Patterson's most powerful tools in peacetime. After the war, he turned this hard-won expertise to a question that had nagged geologists for decades. What precisely was the age of the Earth? Patterson's insight was brilliant in its simplicity. You could not date the Earth directly because the planet's surface is restless. Plate tectonics, volcanism, erosion, and metamorphism had been reworking the rocks for billions of years, resetting their radiometric clocks. The oldest intact rocks on Earth's surface are about 4 billion years old, but the Earth itself was certainly older. However, meteorites, those chunks of rock and metal that fall from the sky, were pristine remnants from the birth of the solar system. They had floated through space, essentially unchanged, since the primordial cloud of gas and dust had coalesced into the sun and its retinue of planets. If you could date the meteorites, you could date the Earth. The problem was lead, specifically lead contamination. Patterson discovered, to his mounting frustration, that lead was absolutely everywhere. In the air, in the water, in the laboratory glassware, in the reagents he used for his analyses, in the solder of the pipes that delivered water to his lab, and even in the dust that settled on his equipment overnight. Every sample he tried to measure was hopelessly contaminated with extraneous lead, making precise isotopic measurements impossible. It took him years to understand that this ubiquitous lead was not natural. It was the legacy of decades of tetrethyl lead being added to gasoline, a practice that had spewed millions of tons of lead into the atmosphere, where it had settled on virtually every surface on the planet. This discovery would eventually lead Patterson on an entirely separate and heroic crusade to ban lead from fuel, paint, and food containers. A fight against powerful industrial interests, most notably the Ethel Corporation, that would last decades and ultimately save countless lives. But first, he needed to eliminate the contamination from his geological samples. At Caltech, where he had moved with his mentor Harrison Brown, Patterson essentially invented the concept of the ultra-clean laboratory. He acid-washed every surface. He distilled every chemical. He sealed every entry point from outside air. He created, from scratch, one of the first truly clean rooms in scientific history, a space so free of lead contamination that it set a new standard for analytical chemistry. In this pristine environment, he analyzed lead isotopes from the Canyon Diablo meteorite, an iron meteorite that was a fragment of the asteroid that had gouged Meteor Crater into the Arizona desert roughly 50,000 years ago. The troilite iron sulfide phase of this meteorite was especially useful because it contained almost no uranium, meaning its lead isotopes had remained essentially unchanged since the solar system formed. Patterson presented his results at a conference in 1955, and in his landmark 1956 paper, he announced the answer. The Earth and the solar system that contained it were 4.55 billion years old, with an uncertainty of about 70 million years. It was a number that has stood essentially unchanged for nearly 70 years. It remains one of the most precisely determined and universally accepted measurements in all of science. The Earth had an age. Now the question became, how old was the universe that held it? To answer that, humanity needed to measure something far more daunting than the age of a rock. It needed to measure the size and expansion rate of the cosmos itself. And that journey would begin with a woman who was paid almost nothing, recognized even less, and whose discovery would change the trajectory of human knowledge forever. In the early 1900s, the Harvard College Observatory was one of the premier astronomical institutions in the world, but it operated on a shoestring budget. Its director, Edward Charles Pickering, had devised an ingenious cost-saving measure. Instead of hiring expensive male astronomers to analyze the thousands of photographic plates accumulating in the observatory's archives, he hired women. They were paid roughly 25 to 50 cents an hour, a fraction of what male astronomers earned, and they were given the title of computer, because that is what the word meant in those days. Not a machine, but a person who computes. The women cataloged stars, measured brightnesses, and classified spectra with painstaking precision. They were sometimes referred to, with casual cruelty, as Pickering's harem. Many of them were brilliant scientists in their own right, but the conventions of the era largely excluded them from the theoretical work that led to recognition and fame. Henrietta Swan Leavitt was born in 1868 in Lancaster, Massachusetts. She had studied at what would become Radcliffe College, where she discovered a passion for astronomy. Leavitt was quiet, methodical, and relentlessly observant. She was also gradually losing her hearing, a condition that worsened throughout her life and may have contributed to her intense focus on visual work. She joined the Harvard Observatory in 1902 and was assigned to study variable stars, stars whose brightness fluctuates over time in rhythmic, predictable patterns. Her specific task was to catalog these variable stars in the Small and Large Magellanic Clouds, two small companion galaxies visible from the southern hemisphere. The photographic plates she examined had been taken at Harvard's outstation in Arequipa, Peru, high in the Andes, where the southern skies were dark and clear night after night. Leavitt bent over her plates with a magnifying loupe, comparing images of the same star taken on different nights, noting which stars brightened and dimmed, and with what regularity. And then she noticed something that nobody else had seen. Among the variable stars she was cataloging were Cepheid variables, a class of pulsating stars named after the prototype Delta Cephei. These stars swell and shrink in a regular heartbeat, brightening as they expand and dimming as they contract. What Leavitt discovered, publishing her initial results in 1908 and her definitive findings in 1912, was a precise mathematical relationship between the period of a Cepheid's pulsation and its intrinsic brightness. Stars that pulsed slowly, taking 30 days to complete a cycle, were genuinely more luminous than stars that pulsed rapidly in just a few days. The relationship was clean, consistent, and unmistakable. This was the cosmic yardstick that astronomy had been desperately waiting for. Here is why it mattered so much. If you know how bright a star truly is, its intrinsic luminosity, and you can measure how bright it appears from Earth, its apparent brightness, then you can calculate its distance. It is the same principle by which you judge how far away a car is at night, by how bright its headlights appear. A distant car's headlights look dim. A nearby car's headlights look bright. If you know the wattage of the bulbs, you can work backward to the distance. Leavitt's period luminosity relation gave astronomers exactly this power. Find a Cepheid variable. Measure how long its brightness cycle takes. Look up the intrinsic luminosity corresponding to that period. Compare with the apparent brightness. Calculate the distance. For the first time, astronomers had a reliable method to measure distances far beyond the reach of the parallax technique, which only worked for relatively nearby stars. Leavitt herself was not permitted to pursue the theoretical implications of her discovery. Pickering kept her focused on cataloging work. She died on December 12, 1921, of stomach cancer at the age of just 53. She never received a Nobel Prize. She was, in fact, nominated posthumously by the Swedish mathematician Gösta Mittag-Leffler in 1925. But the Nobel Committee does not award prizes to the deceased. She never knew the full impact of what she had done. But her discovery would, in the hands of others, become the key that unlocked the size, the age, and the fate of the universe. The first person to use that key would be a former high school teacher, a lawyer, and a boxer who had decided, after years of restless wandering, that what he really wanted to do was look at the stars. Edwin Powell Hubble was born on November 20th, 1889, in Marshfield, Missouri. He was tall, athletic, and impossibly gifted, one of those rare people who seemed to excel at everything they touched. In his youth, he was a standout in basketball, football, track, and boxing, reportedly good enough to have had a shot at a professional fighting career. He earned his undergraduate degree in mathematics and astronomy at the University of Chicago, then crossed the Atlantic to study law at Oxford on a Rhodes Scholarship. Fulfilling the wishes of his father, he returned to the United States, passed the Kentucky bar, and briefly practiced law. But the stars kept calling, and in what may have been the most consequential career change in the history of science, Hubble abandoned his legal career. He taught high school Spanish for a year in Indiana, served in the Army during the First World War, and then went back to the University of Chicago to complete his doctorate in astronomy. In 1919, Hubble joined the staff of the Mount Wilson Observatory. Perched high above the smoky sprawl of Los Angeles on a peak in the San Gabriel Mountains. Mount Wilson was home to the most powerful telescope on Earth. The Hooker telescope, a monster with a 100-inch mirror that could peer deeper into the cosmos than any instrument before it. And it was here, in 1923, that Hubble made the observation that would transform our understanding of the universe. But before we get to Hubble's great discovery, we need to understand the argument he was about to settle. For decades, astronomers had been feuding over the nature of the spiral nebulae, those ghostly pinwheel shapes scattered across the sky. The argument was not merely academic. It concerned the fundamental size and structure of the universe itself. Some astronomers, led by Harlow Shapley of the Mount Wilson Observatory, believed the spiral nebulae were clouds of gas and dust within our own Milky Way. Shapley had recently made a revolutionary discovery of his own. By mapping the distribution of globular clusters, those ancient spherical swarms of hundreds of thousands of stars, he had determined that the Milky Way was far larger than previously thought, roughly 300,000 light-years across, an overestimate. But the right order of magnitude. In Shapley's view, this enormous galaxy was the entirety of the universe. The spiral nebulae were local phenomena, perhaps solar systems in the process of forming. Others, most notably Heber Curtis of the Lick Observatory, believed the spiral nebulae were separate galaxies altogether, entire island universes composed of billions of stars lying at immense distances beyond the Milky Way. Curtis pointed to the occasional appearance of novae in the spiral nebulae, arguing that if these were ordinary stellar explosions seen at enormous distances, the nebulae had to be very far away indeed. The debate came to a head on April 26, 1920, in a packed auditorium at the Smithsonian Institution in Washington, D.C. The event, organized by the National Academy of Sciences, has become known as the Great Debate, and it remains one of the most famous intellectual confrontations in the history of science. Shapley, nervous and somewhat stiff in his delivery, argued for a single enormous galaxy. Curtis, more relaxed and forensic, argued for a universe of many galaxies. The audience included many of the nation's leading scientists, and the result was frustratingly inconclusive. Both men had strong arguments and weak points. Shapley's model explained some observations well, but struggled with others. Curtis's island universe theory was compelling, but lacked the one thing that would have settled the matter instantly: a direct distance measurement to one of the spiral nebulae. Meanwhile, even before this famous debate, a quiet, meticulous astronomer named Vesto Melvin Slipher had been gathering evidence that would prove equally revolutionary, though he would receive far less credit for it. Slipher was born on a farm near Mulberry, Indiana, in 1875. He spent nearly his entire career at the Lowell Observatory in Flagstaff, Arizona, a small institution best known as the personal observatory of Percival Lowell, who had built it primarily to study what he believed were canals on Mars. In 1906, Lowell set Slipher a new task: use the observatory's 24-inch Clark refracting telescope and its spectrograph to study the spectra of the spiral nebulae. Lowell believed these objects were nascent solar systems in the process of forming, and he wanted to know what they were made of and how they were moving. The work was brutally difficult. The spiral nebulae were faint, and capturing their spectra required exposing photographic plates for entire nights, sometimes across multiple consecutive nights. hoping the weather would hold and the telescope tracking would remain steady. By 1912, after years of painstaking improvements to the spectrograph, including replacing the slow original camera lens with a much faster commercial lens, and experimenting with chemical baths to increase the sensitivity of photographic plates, Slipher was finally ready. On the nights of December 29th, 30th, and 31st of 1912, running into the pre-dawn hours of New Year's Day 1913, Slipher captured a sufficiently good spectrum of the Andromeda Nebula. When he measured the resulting plates over the first half of January, he found something astonishing. The spectral lines of the Andromeda Nebula were shifted toward the blue end of the spectrum, indicating that the object was hurtling toward the solar system at a velocity of roughly 300 kilometers per second. This was faster than any astronomical object then known. Slipher kept going. Over the following years, he measured the spectra of dozens more spiral nebulae. By the time of the 1914 meeting of the American Astronomical Society, he had data for 15 of them. Most were not blue-shifted like Andromeda. Most were red-shifted, meaning they were racing away from us. Some were moving at astonishing speeds, over 1,000 kilometers per second. By 1917, he had redshifts for 25 spiral nebulae, and by 1925, he had accumulated data for 45. The pattern was unmistakable, with only a handful of nearby exceptions. The spiral nebulae were fleeing from us in every direction. Slipher himself recognized the significance, noting in his 1917 paper that such enormous velocities implied the nebulae could not be part of the Milky Way, and that our entire stellar system must be moving as a unit through space. Slipher's data would prove indispensable to the revolution that was about to come. But because Slipher worked at a small, somewhat obscure observatory, and because he was modest and publicity-averse by nature, his contributions have been largely overshadowed by the man who used them. Back at Mount Wilson, on the night of October 5th, 1923, Edwin Hubble exposed a photographic plate of the Andromeda Nebula through the Great Hooker telescope. When he developed the plate, he found what appeared to be a nova, a star that had suddenly flared in brightness. He marked it on the plate with the letter N. But when he compared his plate to earlier photographs, he realized the star was not a nova at all. It was brightening and fading in a regular, rhythmic pattern. It was a Cepheid variable. In a moment that he would later mark on the plate itself, Hubble crossed out the N and wrote VAR for variable. He had found a Cepheid variable star in the Andromeda Nebula. And using Henrietta Leavitt's period luminosity relation, he could now calculate its distance. The answer was staggering. Andromeda was roughly 900,000 light-years away, far, far beyond the boundaries of the Milky Way. This initial estimate was too low by about a factor of 2.5 due to errors in the distance calibration that would take decades to correct. But even the wrong number was transformative. The great debate was over. Curtis had been right. The universe was suddenly, shockingly, unimaginably larger than anyone had believed. The spiral nebulae were not clouds of gas within our galaxy. They were galaxies in their own right, each one a vast island of hundreds of billions of stars, separated by gulfs of emptiness so vast that light itself takes millions of years to cross them. Hubble announced his results in January 1925 at a meeting of the American Astronomical Society, and the scientific world was forever changed. Shapley, who had staked his reputation on the Milky Way being the entire universe, reportedly received a letter from Hubble containing the evidence and told a colleague, "Here is the letter that has destroyed my universe." Hubble did not stop there, working with the tireless Edwin Hubble, a man with one of the most remarkable careers in the history of astronomy. Hubble began systematically measuring the distances to more and more galaxies. Hubble had started at Mount Wilson as a mule driver, hauling construction materials up the mountain for the observatory's telescopes. He had no formal education beyond the 8th grade, but he had steady hands, infinite patience, and an almost supernatural gift for the agonizing work of long-exposure photography. Sitting for hours in freezing cold at the eyepiece of the telescope, making minute corrections to keep the image steady on the photographic plate as the Earth turned beneath him, he became one of the most skilled observational astronomers of his generation. And his partnership with Hubble was one of the great scientific collaborations of the 20th century. And in 1929, Hubble published the result that would change everything. In a paper in the Proceedings of the National Academy of Sciences, he plotted the distance to each galaxy against its recession velocity, using his own Cepheid-based distances combined with the redshift measurements that Slipher and others had been gathering for years. The data points were scattered and imperfect, but the trend was unmistakable. He had found a direct, linear relationship between the distance to a galaxy and the speed at which it was receding from us. The farther away a galaxy was, the faster it was moving away. This was not a random pattern. It was a law. Velocity equals distance multiplied by a constant. Double the distance, and you doubled the recession speed. Triple it, and the speed tripled. The implications were staggering, and they went far beyond mere astronomy. This relationship, now known as the Hubble-Lemaître law, was the observational evidence for something that theorists had already predicted, but few had dared to believe. The universe was expanding, and not in the way you might first imagine. The galaxies were not flying apart through space like shrapnel from an explosion. Space itself was stretching, expanding uniformly in all directions, carrying the galaxies along with it. The analogy most often used, imperfect but useful, is a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. A raisin that is close to you moves away slowly. A raisin that is far away moves away quickly because there is more dough between you expanding. No raisin is at the center. The expansion is happening everywhere, at every point, all at once. And here is the breathtaking implication. If the universe is expanding now, then it must have been smaller in the past. Run the expansion backward, like rewinding a film, and the galaxies move closer together. The universe becomes denser, hotter, and more compressed. Keep rewinding, and eventually you reach a moment when everything, all of space, all of matter, all of energy, the raw material of every galaxy, every star, every planet, every atom in your body, was compressed into an inconceivably dense, inconceivably hot point. There must have been a beginning, a moment of creation, a cosmic birthday. The universe had a birthday, and now humanity had a way to calculate it. The person who first understood what an expanding universe truly meant was not Edwin Hubble. It was a Belgian priest. Georges Henri Joseph Edouard Lemaitre was born on July 17, 1894, in Charleroi, Belgium, an industrial city scarred by coal mines and factory smoke. He was a man of seemingly irreconcilable vocations, a brilliant mathematician, a gifted physicist, and a devoutly ordained Catholic priest. He studied civil engineering at the Catholic University of Leuven before the First World War erupted and consumed his youth. Lemaitre served as an artillery officer in the Belgian army and witnessed some of the most horrific fighting of the conflict, including the first use of poison gas. After the armistice, he returned to his studies with fierce intensity, pursuing both physics and theology simultaneously. He was ordained as a priest in 1923, and in the same year, traveled to Cambridge, England, to study with the distinguished astronomer Arthur Eddington, who recognized Lemaitre's exceptional talent immediately. But Lemaitre's great intellectual debt was not to Eddington alone. It was also to a man who had died years before they could ever meet, the Russian mathematician Alexander Friedmann. In 1922, working in the newly renamed city of Petrograd, in a Russia still reeling from revolution and civil war, Friedmann had taken Einstein's field equations of general relativity, the mathematical framework describing how matter and energy curve the fabric of space-time, and solved them for the case of a homogeneous, isotropic universe. What he found was remarkable and deeply unsettling. Einstein had assumed, as virtually everyone did at the time, that the universe must be static, unchanging in its overall structure. The idea that the cosmos was in motion, expanding or contracting as a whole, seemed absurd. Einstein was so committed to a static universe that he had added an extra term to his equations, a mathematical fudge factor he called the cosmological constant, represented by the Greek letter lambda. This term acted as a kind of anti-gravity, a repulsive force woven into the fabric of space itself, whose sole purpose was to exactly counterbalance the attractive pull of gravity and hold the universe in a perfectly balanced, motionless state. But Friedmann showed that this balancing act was inherently unstable, like a pencil balanced on its point. Drop the cosmological constant, and the equations described a universe that was dynamic, alive with motion. It could be expanding, it could be contracting, it could oscillate between the two, pulsing like a cosmic heartbeat. The one thing it absolutely could not do, according to the pure mathematics of general relativity, was stand still. Einstein initially dismissed Friedmann's work, writing a curt note to the journal claiming the Russian had made a mathematical error. Friedmann wrote back, politely but firmly, proving that no error existed. Einstein grudgingly conceded the mathematics, but still rejected the physical implications. And then, tragically, Friedmann died of typhoid fever in 1925, at the age of just 37. He never lived to see his equations vindicated. Lemaitre, working independently and apparently unaware of Friedmann's earlier work, arrived at similar solutions in 1927. But Lemaitre went further than Friedmann had, much further. While Friedmann had been content to explore the mathematical possibilities of dynamic universes, Lemaitre was determined to connect theory to observation. He combined the theoretical predictions of an expanding universe with actual observational data, drawing on Slipher's redshift measurements, distance estimates for galaxies derived from Hubble's early work, and his own theoretical analysis. The result was a paper published in French in an obscure Belgian academic journal, the Annales de la Société Scientifique de Bruxelles, in 1927. In this paper, Lemaitre not only demonstrated that the universe was expanding, but also calculated the rate of expansion, deriving a value for what we would now call the Hubble constant, a full 2 years before Hubble's own landmark publication. The paper should have been a bombshell. It was ignored. Lemaitre sent a copy to his former mentor, Eddington. Eddington either did not read it carefully or did not grasp its significance. He set it aside. Lemaitre also sent a copy to Einstein, whom he met at the 1927 Solvay conference in Brussels. Einstein studied the mathematics and acknowledged it was correct. But he was unmoved by the physical conclusions. He told Lemaitre, with characteristic bluntness, that his physics was abominable. Coming from the man who had invented general relativity, it was a crushing dismissal. The paper sank without a trace, buried in a journal that few astronomers outside of Belgium would ever read. It was not until 1931, after Hubble's observational evidence for the expansion had become widely known, and after Eddington had independently arrived at similar conclusions about the instability of Einstein's static universe, that Eddington finally realized his former student had anticipated everything. Embarrassed, he arranged for Lemaitre's paper to be translated into English and published in the monthly notices of the Royal Astronomical Society. But strangely, the key paragraph in which Lemaitre had calculated the expansion rate was omitted from the translation. For decades, historians suspected foul play. Perhaps Eddington had suppressed the paragraph to protect Hubble's priority, or perhaps Hubble himself had exerted influence. But in 2011, the historian of science Mario Livio discovered a letter from Lemaitre in which the priest explained that he himself had removed the paragraph. The observational data he had used was no longer current, he wrote, and Hubble's more recent and precise measurements had superseded his own. It was a characteristically selfless act from a man who appeared to care far more about truth than about personal glory. Lemaitre's most radical and most consequential idea came later that same year, in 1931, when he published a brief but extraordinary paper in the journal Nature, running just a single page. It contained an idea of almost incomprehensible ambition. In it, Lemaitre proposed that if the universe was expanding, then tracing the expansion backward in time meant that the cosmos must once have been compressed into an incredibly small, incredibly dense, and incredibly hot state. He called this original state the primeval atom, a single quantum, a cosmic egg from which the entire universe had hatched in a moment of supreme creative violence. It was the first truly scientific articulation of what we now call the Big Bang, though that name would not be coined for another 18 years, and would come, ironically, from the theory's greatest critic, Einstein, who had spent years resisting the implications of his own equations, the very equations that naturally predicted a dynamic cosmos, eventually came around. In 1933, after attending a series of lectures by Lemaitre at the California Institute of Technology in Pasadena, Einstein is reported to have stood before the assembled audience and declared, "This is the most beautiful and satisfactory explanation of creation to which I have ever listened." He later called his introduction of the cosmological constant the fudge factor he had added to prevent his equations from predicting exactly what Lemaitre and Friedman had shown they predicted. The biggest blunder of his career. The exact provenance of the biggest blunder, quote, is somewhat murky, with some historians attributing it to George Gamo's recollections rather than to a direct written record. But the sentiment is beyond dispute. Einstein had been wrong to assume a static universe, and Lemaitre, the quiet Belgian priest, had been right to envision a dynamic, evolving, expanding cosmos with a definite beginning. But here was the problem, and it was a serious one. If the universe was expanding at a measurable rate, you could, in principle, calculate its age by simply running the expansion backward and asking, how long ago was everything in the same place? Hubble's original 1929 data implied an expansion rate of roughly 500 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. At this rate, the universe would be only about 2 billion years old, and that was a disaster. By the 1930s, geologists using radiometric dating had already established that the Earth was at least 3 billion years old, with some rock samples pushing toward 4 billion. The universe appeared to be younger than the planet sitting inside it. It was like finding a birth certificate that says the mother is younger than the child. Something had to be wrong. For 2 decades, this age problem hung over cosmology like a storm cloud. Critics of the Big Bang Theory, including Fred Hoyle and the Steady State camp, seized upon it gleefully. How could anyone take the expanding universe seriously if it couldn't even get the ages right? The error was not in the concept. It was in the calibration, specifically in the measurement of cosmic distances. Hubble's distance scale was off, and it would take a generation of astronomers to fix it. The man who made the first and most dramatic correction was Walter Baade, a German-born astronomer working at Mount Wilson during the Second World War. Baade was a meticulous observer who had been classified as an enemy alien during the war and confined to the Los Angeles area. Unable to serve in the military or travel freely, he was, however, allowed to use the Great Hooker telescope, and with most of the observatory staff away on war service, the surrounding city blacked out against potential Japanese air raids, and the skies over Mount Wilson darker than they had been in years. Baade had extraordinary observing conditions, largely to himself. He used these conditions to study the stars of the Andromeda galaxy with unprecedented depth and detail. What Baade discovered in 1952 transformed cosmology. He found that there were actually 2 distinct populations of Cepheid variables, each with a different period luminosity relationship. The population 1 Cepheids, younger stars found in the spiral arms of galaxies, were genuinely brighter than the population 2 Cepheids, older stars found in globular clusters, which Hubble had inadvertently used as his calibration standard. Hubble had been comparing apples and oranges, using the wrong brightness calibration for the Cepheids he observed in distant galaxies. When Baade applied the correct calibration, the distances to all extragalactic objects roughly doubled overnight. The Andromeda galaxy jumped from 900,000 to nearly 2 million light years. And the age of the universe leaped from 2 billion years to somewhere between 3 and 5 billion, resolving the worst of the age paradox at a single stroke. Further refinements followed over the next several decades, as astronomers painstakingly improved every rung of the cosmic distance ladder. Alan Sandage, widely regarded as Hubble's intellectual heir and the most influential observational cosmologist of the second half of the 20th century, spent his entire career at the Mount Wilson and Palomar observatories refining the expansion rate. Sandage was meticulous, cautious, and fiercely protective of his data. He consistently found a relatively low expansion rate, around 50 kilometers per second per megaparsec, implying a universe roughly 20 billion years old. His work was challenged, sometimes bitterly, by the French-American astronomer Gerard de Vaucouleurs, who used different distance indicators and different calibration techniques, and consistently found a much higher expansion rate, around 100 kilometers per second per megaparsec, implying a universe only about 10 billion years old. The dispute between these two camps, sometimes called the Hubble Wars, was one of the longest and most contentious in the history of observational astronomy. It divided the field into rival factions for decades, with each side questioning the other's methods, assumptions, and even scientific integrity. The controversy would not be resolved until the late 1990s and early 2000s, when new space-based instruments finally provided the precision needed to settle the debate. In 2018, the International Astronomical Union voted to rename Hubble's law as the Hubble-Lemaître law, formally acknowledging the Belgian priest's priority in predicting and calculating the expansion of the universe. It was a recognition long overdue, a quiet act of justice across the decades for a man who had been too modest to fight for his own credit. But to truly pin down the age of the universe, astronomers needed more than just the expansion rate. They needed a detailed understanding of the composition and geometry of the cosmos. They needed to know what the universe was made of and how its expansion had changed over time. And the key to all of this was hiding in the faint hiss of radiation that permeates every corner of the sky. The origin of that radiation stretches back to a prankster who escaped the Soviet Union in a kayak. George Gamow was born Georgy Antonovich Gamov on March 4, 1904, in the city of Odessa, then part of the Russian Empire, on the northern shore of the Black Sea. He was brilliant, irreverent, and endlessly inventive, a physicist with the soul of a comedian and the courage of an adventurer. He peppered his scientific papers with jokes, puns, and whimsical asides. He illustrated his popular science books with his own cartoons. He stood 6 feet 3 inches tall, spoke with a thick Russian accent that he never lost, and had a famously booming laugh that could be heard across a lecture hall. He once crafted a fake paper entirely as a gag, purporting to be authored by the famous physicist Hans Bethe, just so the paper's author list would read Alpha, Bethe, Gamow, a play on the first 3 letters of the Greek alphabet, alpha, beta, and gamma. That joke concealed one of the most important scientific triumphs of the 20th century. Gamow had made fundamental contributions to nuclear physics early in his career, including the first quantum mechanical explanation of radioactive alpha decay, a theory he developed at the age of just 24. But by the early 1930s, life in the Soviet Union had become increasingly difficult for scientists. The government expected researchers to align their work with Marxist ideology, and travel to international conferences was severely restricted. Gamow, desperate to pursue his science freely, hatched an audacious escape plan. In the summer of 1932, he and his wife, Lyuba Vokmintseva, loaded a small kayak with provisions and attempted to paddle across the Black Sea toward Turkey, a distance of roughly 170 miles of open water. The weather turned against them. After battling waves and wind for several desperate days, they were forced to turn back, barely making it to shore alive. A second attempt, this time aiming for Norway across the Barents Sea, also failed. Eventually, in 1933, Gamow managed to attend the Solvay conference in Brussels by obtaining exit visas through a combination of diplomatic maneuvering and sheer persistence. Once outside the Soviet Union, he and his wife simply did not return. he settled in the United States, where he became a professor at George Washington University in Washington, D.C., and threw himself with characteristic gusto into a new problem: the origin of the chemical elements. In the late 1940s, Gamow and his doctoral student Ralph Alpher developed a theory that the light elements, hydrogen, helium, and trace amounts of lithium and beryllium, had been forged in the intense heat of the early universe during the first few minutes after the Big Bang. This process, which Gamow called the Big Squeeze, and which we now call Big Bang nucleosynthesis, predicted that the universe should be roughly 75% hydrogen and 25% helium by mass, with only tiny traces of heavier elements. This prediction turned out to be spectacularly accurate. Their landmark paper was published on April 1st, 1948. Gamow could not resist one final joke. He added Hans Bethe's name to the author list without asking, purely for the alpha beta gamma pun. Bethe, by all accounts, was amused. The paper has been known ever since as the alpha beta gamma paper, or simply the Alpher-Bethe-Gamow paper. But for Ralph Alpher, who had done the lion's share of the actual calculations as his doctoral dissertation, the joke stung. Having his thesis appear to be co-authored by two of the most famous physicists in the world undermined his own contribution. He would struggle for recognition for the rest of his career. Alpher and his colleague Robert Herman made another prediction that year, one even more consequential than the elemental abundances. If the early universe had been incredibly hot and dense, they reasoned, then it should have been flooded with radiation, a blinding sea of photons in thermal equilibrium with the surrounding matter. As the universe expanded and cooled, that radiation would have cooled along with it, its wavelengths stretching out from the visible and ultraviolet into the microwave range. Alpher and Herman calculated that this relic radiation should still permeate the universe today, filling all of space with a faint glow corresponding to a temperature of roughly 5 degrees above absolute zero, 5 Kelvin. It was an astonishing prediction, and it was almost completely ignored. While Gamow, Alpher, and Herman were working out the details of the hot Big Bang, a rival theory was taking shape across the Atlantic. In 1948, the same year as the Alpher-Bethe-Gamow paper, 3 physicists at Cambridge University proposed an alternative model for the cosmos, one that required no beginning at all. Fred Hoyle, Herman Bondi, and Thomas Gold had reportedly been inspired by a British horror film called Dead of Night, a 1945 anthology movie with a brilliantly unsettling circular plot structure in which the final scene seamlessly loops back to the opening scene, so that the story has no true beginning and no true end. After watching the film together one evening, the 3 physicists found themselves wondering, what if the universe were like that? What if it had no beginning and no ending? What if it simply existed, eternally and unchangingly, recycling itself forever? Their answer was the steady-state theory, published in 1948. The core idea was both simple and audacious. Yes, the universe was expanding, they agreed. Hubble's observations were beyond dispute. But the expansion did not mean the cosmos had started from a dense, hot beginning. Instead, as the universe expanded and existing galaxies spread farther apart, new matter was continuously created in the growing gaps between them. Fresh hydrogen atoms, they proposed, were popping into existence out of nothing, spontaneously materializing in the void over millions of years. This new matter would gradually accumulate under gravity, condensing to form new stars and new galaxies to replace the ones receding into the distance. The required rate of matter creation was astonishingly small, roughly 1 hydrogen atom per cubic meter of space every 300,000 years. That works out to about 1 atom per year in a volume the size of a large sports stadium. It was far, far too little to be detected directly by any instrument, which made the theory frustratingly difficult to test. The universe, in this model, would always look essentially the same on the largest scales, no matter when you observed it. It had no beginning, no end, and no special moment of creation. It simply persisted, renewing itself endlessly, like a river that flows forever. The steady-state theory was elegant, parsimonious, and deeply appealing to many scientists who were uncomfortable with the philosophical and theological overtones of a universe that had a definite moment of creation. Hoyle, in particular, was a fierce advocate. He was also, by a considerable margin, the most publicly visible astronomer of his generation. In 1949, during a BBC radio broadcast, Hoyle used a phrase to describe the rival theory that would stick forever. He called it the Big Bang. Whether he intended the name to be dismissive is still debated, but the label caught on, and the supporters of the primeval atom theory eventually embraced it. The battle between the Big Bang and the steady state would dominate cosmology for nearly 2 decades. It was one of the great scientific controversies of the 20th century, argued with passion, and sometimes with personal animosity in lecture halls, journal pages, and BBC studios. Observations provided ammunition for both sides, and the debate forced astronomers to sharpen their tools, and their thinking in ways that advanced the field enormously. The British radio astronomer Martin Ryle, working at the Cavendish Laboratory in Cambridge, conducted systematic surveys of radio sources across the sky throughout the 1950s. His results struck at the heart of the steady-state theory. Ryle found that faint radio sources, which were distant objects being observed as they existed billions of years ago, were significantly more numerous than bright, nearby sources. If the universe were truly in a steady state, unchanging over time, then the density of radio sources should be the same at all distances and at all epochs. But Ryle's surveys showed the opposite. There were more radio sources per unit volume in the distant, ancient universe than in the nearby, recent universe. The cosmos was different in the past. It had evolved. This directly contradicted the steady state's central prediction of an unchanging cosmos. Hoyle fired back vigorously, questioning Ryle's data, his calibration methods, and his statistical analysis. The arguments grew heated, sometimes descending into personal attacks. At one point, the rivalry between the Cambridge radio astronomers and the Cambridge theorists became so intense that colleagues described the atmosphere as poisonous. But as Ryle's surveys improved and his data accumulated, his case grew steadily stronger. The decisive evidence would not come from radio surveys or theoretical arguments. It would come from 2 bewildered engineers and a flock of pigeons. In the spring of 1964, 2 young radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey. In a pastoral countryside of rolling hills, about 30 miles south of New York City, they had been given access to a remarkable instrument, a 20-foot horn-shaped radio antenna that looked like an enormous metal ear turned toward the sky. It had been built for Project Echo, NASA's early satellite communications experiment, in which radio signals were bounced off large metallic balloons orbiting the Earth. By 1964, the ECHO project was winding down, and newer satellite technology had made the horn antenna obsolete for communications. But for radio astronomy, the antenna was a treasure. It was extraordinarily sensitive and had the additional advantage of being designed to minimize interference from stray signals. Penzias and Wilson wanted to use it to map faint radio emissions from the Milky Way. They knew that to do this, they would first need to account for every possible source of background noise in the antenna. They expected to find some from the atmosphere, from the ground, and from the instrument's own electronics. What they did not expect was a mysterious, unexplained hiss that refused to go away. From the very first observations, the signal was there. No matter where they pointed the antenna, north or south, east or west, toward the galactic plane or away from it, day or night, summer or winter, they detected a persistent, uniform buzz of microwave radiation at a wavelength of about 7.3 centimeters. It was faint, but unmistakable. It came from everywhere equally, with no variation in direction. And they could not account for it. They checked and rechecked their equipment with the thoroughness of engineers whose careers depended on precision instrumentation. They tightened every bolt and every waveguide connection. They cooled the antenna's sensitive receiver to cryogenic temperatures to reduce electronic noise. They accounted for radiation from the atmosphere, from the ground, and from the antenna's own structure. And then they discovered a more prosaic problem. A pair of pigeons had nested inside the horn of the antenna and had coated its interior surface with what Penzias would later diplomatically describe as a white dielectric material. In less delicate language, the pigeons had covered the instrument with droppings. Penzias and Wilson carefully trapped the birds, placed them in a shipping container, drove them 30 miles away, and released them. The pigeons flew straight back. They trapped them again. Eventually, the pigeons were, in Penzias's understated words, dealt with by more permanent means. The droppings were meticulously cleaned out. The hiss remained. It was everywhere. It was uniform. It was a temperature of about 3.5 Kelvin. And Penzias and Wilson had absolutely no idea what it was. Meanwhile, less than 40 miles away at Princeton University, a team led by the physicist Robert Dicke had independently predicted almost exactly this signal. Dicke and his colleagues, including Jim Peebles, Peter Roll, and David Wilkinson, had reasoned from first principles, essentially reinventing the prediction that Alpher and Herman had made, and that Gamow had championed nearly 2 decades earlier. That if the Big Bang had occurred, the universe should be filled with relic radiation at a temperature of a few degrees Kelvin. They were actually in the process of building their own antenna to search for it when they received a phone call from Penzias and Wilson. The story of that phone call has become one of the most famous anecdotes in the history of science. Dicke had been on his own hunt for this radiation, motivated by a line of theoretical reasoning that had, unknown to him, been anticipated by Gamow, Alpher, and Herman nearly 2 decades earlier. The irony was painful. An entire generation of cosmologists had essentially forgotten the Alpher-Herman prediction. Textbooks did not mention it. The physics community had moved on to other problems, and so Dicke's group at Princeton had reinvented the prediction from scratch, unaware that the answer had been sitting in the scientific literature since 1948. When the phone call came from Bell Labs, Dicke hung up the receiver, turned to his colleagues, and said simply, "Boys, we've been scooped." Two papers were published simultaneously in the Astrophysical Journal in 1965. Penzias and Wilson's paper was a model of careful, understated science. It reported a measured excess antenna temperature of 3.5 Kelvin, isotropic and unpolarized, for which they could find no explanation. Dick's accompanying paper provided the explanation. This was the cosmic microwave background radiation, the cooled remnant of the primordial fireball, the afterglow of the Big Bang itself. To understand what this radiation actually is, you need to picture the universe roughly 380,000 years after the Big Bang. Before that moment, the cosmos was a blinding fog. The temperature was so high that atoms could not exist. Every time a proton captured an electron, a passing photon would immediately knock the electron free again. Photons could not travel more than a short distance before being scattered by the free electrons that filled the universe. Space was opaque, like being inside a cloud. But as the universe expanded and cooled, the temperature eventually dropped below roughly 3,000 Kelvin. At that point, for the first time in cosmic history, electrons were captured by protons and stayed captured. Atoms formed, hydrogen atoms mostly with some helium. And suddenly, with no more free electrons to scatter them, the photons were free. Light decoupled from matter and streamed out in every direction. The universe became transparent. That first light has been traveling ever since. Its wavelengths stretched by the expansion of space from the visible spectrum into the microwave range, cooling from 3,000 Kelvin to the roughly 2.7 Kelvin we measure today. When you see static on an old, untuned television set, roughly 1% of that fuzzy snow is caused by photons from the cosmic microwave background. You are literally watching the afterglow of creation. The discovery of the CMB was devastating for the steady-state theory. The radiation was exactly what the Big Bang predicted, and exactly what the steady state could not explain. Hoyle fought back for years, proposing various mechanisms by which the radiation could be produced in a steady-state universe. But none of his alternatives held up under scrutiny. The scientific community moved overwhelmingly toward the Big Bang. By the end of the 1960s, the steady-state theory was, for all practical purposes, dead. Hoyle never accepted this verdict. He spent the rest of his career developing increasingly elaborate alternatives to the Big Bang, none of which gained significant traction among the broader physics community. He died in 2001, still a skeptic of the theory whose name he had inadvertently coined. Ironically, Hoyle's other major contribution to astrophysics was absolutely correct and monumentally important. He was the primary architect of the theory of stellar nucleosynthesis, the detailed explanation of how elements heavier than lithium are forged inside the cores of stars through nuclear fusion, and then scattered across the cosmos by supernova explosions. In a landmark 1957 paper, commonly known as B²FH after the initials of its four authors, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Hoyle, the team laid out a comprehensive framework showing how the periodic table of elements was built up inside successive generations of stars. It is one of the most cited and influential papers in the history of astrophysics. Many scientists believe this work deserved a Nobel Prize. When the 1983 Nobel Prize in Physics was awarded for nucleosynthesis work, it went to Hoyle's collaborator William Fowler, but not to Hoyle himself. the omission remains one of the most debated and controversial in Nobel history, with many suspecting that Hoyle's abrasive personality and his vocal criticism of the scientific establishment had cost him the prize. Penzias and Wilson received the 1978 Nobel Prize in Physics for their discovery. Dick's team, which had predicted the signal and explained its significance, received nothing. Jim Peebles, the theoretician who had done much of the key computational work, would have to wait another 4 decades. In 2019, at the age of 84, Peebles was finally awarded the Nobel Prize in Physics for his theoretical contributions to cosmology. The committee cited his work spanning more than 50 years, from the prediction of the CMB to the development of the modern framework for understanding the large-scale structure of the universe. When asked at the press conference what his discovery meant, Peebles replied with characteristic modesty that he preferred the word exploration to discovery. He said, "It is a thing that I am very much disturbed about, that we have this wonderfully complete theory of the physical cosmos, and yet most of it is unknown." The cosmic microwave background told scientists that the Big Bang had happened, but to determine when it had happened, to measure the age of the universe with precision, they needed to study the CMB in far greater detail. They needed to see its imperfections. And for that, they needed to leave the ground. For more than 2 decades after Penzias and Wilson's discovery, the cosmic microwave background appeared to be perfectly smooth. Every measurement, from every direction, returned the same temperature, roughly 2.7 Kelvin, uniform to an extraordinary degree. This was reassuring in one sense, because it confirmed the Big Bang prediction of a hot, dense, early universe. But it was also deeply troubling. If the early universe had been perfectly smooth, with matter distributed absolutely evenly in every direction, then there would have been no reason for gravity to pull matter together into clumps. Without clumps, there would be no galaxies, no stars, no planets, no people staring at static on television screens and wondering about the origin of the cosmos. The universe should have remained a featureless, diffuse fog of hydrogen gas forever. Clearly, the early universe was not perfectly smooth. There had to be tiny variations in temperature and density, subtle ripples imprinted on the primordial plasma that served as the seeds of all future cosmic structure. Gravity would have amplified these seeds over billions of years, pulling slightly denser regions together to form the first galaxies and galaxy clusters. But these variations had to be incredibly small, so small that ground-based and balloon-based instruments could not detect them. Detecting them would require a satellite. George Smoot was a young physicist at Lawrence Berkeley National Laboratory in California when he first proposed, in 1974, a satellite mission to map the cosmic microwave background with unprecedented precision. The idea eventually became the Cosmic Background Explorer, known as COBE. It was a collaboration between NASA and a large team of scientists, led by Smoot on the instrument designed to detect temperature variations, the Differential Microwave Radiometer, or DMR, and by John Mather on the instrument designed to measure the overall spectrum of the CMB. The Far Infrared Absolute Spectrophotometer, or FIRAS. The path from concept to launch was agonizingly slow. The satellite was originally designed to be launched aboard the Space Shuttle. But on January 28, 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew members. The tragedy grounded the shuttle fleet and forced the Kobe team to redesign their satellite for a smaller Delta rocket. It took years. Finally, on November 18, 1989, Kobe roared into orbit. The FIRAS instrument produced results almost immediately, and they were spectacular. It measured the spectrum of the cosmic microwave background with extraordinary precision and found a perfect blackbody curve, the most perfect blackbody spectrum ever measured in nature. A blackbody is an idealized object that absorbs all radiation and re-emits it in a characteristic pattern determined solely by its temperature. The fact that the CMB spectrum was a flawless blackbody was a powerful confirmation that it originated in the hot, dense conditions of the early universe. When Mather presented the FIRAS spectrum at the January 1990 meeting of the American Astronomical Society, the audience gave him a standing ovation, a reaction virtually unheard of at a scientific conference. But the real prize was the DMR results, and they took longer. For months, Smoot and his team painstakingly analyzed the DMR data, searching for the faint temperature fluctuations that had to be there. The variations they were looking for were tiny, roughly 1 part in 100,000, or about 10 millionths of a degree. Teasing out such minuscule signals from the noise of the instrument, the microwave emissions of the galaxy, and other contaminating sources was a monumental challenge. On April 23, 1992, Smoot announced the results at a meeting of the American Physical Society in Washington, D.C. The DMR had detected the fluctuations. They were there, faint ripples in the temperature of the cosmic microwave background, imprinted on the sky when the universe was just 380,000 years old. These tiny variations, measuring about 1 part in 100,000, or roughly 30 millionths of a degree, formed a mottled pattern of slightly warmer and slightly cooler spots spread across the entire sky. The warmer spots corresponded to regions where matter was very slightly denser in the early universe. The cooler spots corresponded to regions that were slightly less dense. Over the next 13 billion years, gravity would amplify these minuscule differences, pulling the denser regions together to form filaments and walls and clusters of galaxies, while the less dense regions expanded into the enormous voids that separate them. Every galaxy in the universe, every star, every planet, every living thing traces its ancestry back to one of those faint, warm spots in the Kobe map. The scientific world erupted with excitement. Stephen Hawking, when informed of the result, called it the greatest discovery of the century, if not of all time. Smoot's own characterization was more poetic. If you're religious, it's like seeing the face of God. The comparison resonated widely because these fluctuations were, in a very real sense, the oldest structures in the universe, the primordial pattern from which all subsequent complexity would emerge. John Mather and George Smoot shared the 2006 Nobel Prize in Physics for their work on Kobe. Mather was cited for the FIRAS measurement of the perfect blackbody spectrum, and Smoot for the DMR detection of the anisotropies. Together, they had given humanity its first real look at the infant universe, a portrait taken when the cosmos was less than 400,000 years old. But Kobe's portrait was blurry. Its angular resolution was about 7 degrees, meaning it could see large-scale features, but not the fine details hidden within them. To truly decode the message encoded in the cosmic microwave background, to extract from it the precise age, composition, and geometry of the universe, astronomers needed a much sharper picture. they were about to get one. On June 30th, 2001, a small satellite called the Wilkinson Microwave Anisotropy Probe, known as WMAP, launched from Cape Canaveral atop a Delta rocket and headed for a point in space about 1.5 million kilometers from Earth, a gravitationally stable location known as the second Lagrange point, or LTWO. From there, shielded from the heat of the sun, the Earth, and the Moon, WMAP would stare at the cosmic microwave background with 35 times the sensitivity and 33 times the angular resolution of COBE. What WMAP found was extraordinary. The map it produced was a masterpiece of cosmological information. The temperature fluctuations in the CMB were not random. They showed a pattern, a specific set of peaks and valleys in what physicists call the power spectrum. These peaks corresponded to sound waves, literal acoustic oscillations that had reverberated through the primordial plasma before the universe became transparent. Here is what that means, and it is one of the most remarkable things in all of physics. In the early universe, before atoms formed, the cosmos was filled with a hot, dense soup of photons, electrons, and protons, intermixed with dark matter and neutrinos. This soup was not static. It was alive with competing forces. Gravity, exerted primarily by the dark matter, tried to pull the ordinary matter together into clumps, compressing it into denser and denser concentrations. But the intense radiation pressure from the enormous number of photons in the plasma pushed back furiously against this compression, resisting the gravitational collapse. These two opposing forces, gravity pulling inward and radiation pressure pushing outward, created oscillations. Regions of matter would compress under the pull of gravity, heat up, then bounce back as radiation pressure overwhelmed the gravitational attraction, then compress again as gravity reasserted itself. The matter sloshed back and forth, oscillating like a bell that had been struck or like the sound waves reverberating inside a musical instrument. Different-sized regions oscillated at different frequencies, just like organ pipes of different lengths produce different musical notes. Larger regions oscillated more slowly. Smaller regions oscillated more rapidly. The result was a symphony of sound waves, literal acoustic oscillations reverberating through the entire universe, at a time when the cosmos was small enough and dense enough for sound waves to propagate across vast distances. When the universe cooled enough for atoms to form, at roughly 380,000 years of age, the music stopped. The oscillations were frozen in place, locked into the pattern of the cosmic microwave background as patterns of slightly hotter and slightly cooler spots, like a photograph of a drum skin captured at a single instant while vibrating. The sizes of these spots and the relative heights of the peaks and valleys in the power spectrum encode an astonishing wealth of information about the composition, geometry, age, and fate of the universe. By analyzing these peaks, the WMAP team was able to determine, with remarkable precision, that the geometry of the universe is flat, meaning parallel lines remain parallel even across cosmic distances. They determined that the universe is composed of approximately 5% ordinary matter. The protons, neutrons, and electrons that make up everything you can see and touch, about 27% dark matter, a mysterious substance that exerts gravitational pull but does not interact with light, and about 68% dark energy, an even more mysterious component that is driving the accelerated expansion of the universe. This last ingredient, dark energy, had been discovered just a few years earlier, in 1998, in what many regard as the most shocking observational result in the history of modern cosmology. Two independent teams of astronomers, the Supernova Cosmology Project led by Saul Perlmutter of Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team led by Brian Schmidt, and including Adam Rees, had been studying distant Type 1a supernovae. These titanic stellar explosions are useful cosmological tools because they all reach approximately the same peak brightness, making them excellent standard candles for measuring cosmic distances. Both teams had set out to measure the rate at which the expansion of the universe was slowing down. After all, gravity should be putting the brakes on the expansion, pulling the galaxies back toward each other. The only question, they thought, was how quickly the deceleration was occurring. But when they analyzed their data, both teams independently arrived at the same astonishing conclusion. The supernovae were dimmer than expected. They were farther away than they should have been if the expansion were slowing down. The expansion of the universe was not decelerating. It was accelerating. Something was pushing the cosmos apart faster and faster, something invisible, pervasive, and profoundly mysterious. It was given the appropriately enigmatic name dark energy, and it constitutes roughly 68% of the total energy content of the universe. Nobody knows what it is. Nobody has a compelling theoretical explanation for it. It is one of the deepest unsolved problems in all of physics. The discovery earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics. WMAPS measurements, combined with the supernova data and other observations, allowed cosmologists to calculate the age of the universe with unprecedented accuracy. The result, 13.772 billion years, with an uncertainty of about 59 million years. For the first time, humanity could state the age of the cosmos to a precision of better than 1%. But even WMAP was not the final word. On May 14, 2009, the European Space Agency launched the Planck satellite from French Guiana, named after the German physicist Max Planck, the father of quantum theory. Like WMAP, Planck was sent to the Eltwo-Lagrange point, that gravitationally stable perch 1.5 million kilometers from Earth. But Planck represented a quantum leap forward in technology and sensitivity. Its most advanced detectors, known as bolometers, were cooled by a sophisticated multi-stage refrigeration system to just 1/10 of a degree above absolute zero, or roughly 100 millikelvin. At that temperature, the detector's own thermal vibrations were reduced to almost nothing, making them extraordinarily sensitive to the faint temperature variations in the CMB. Planck observed the sky in 9 separate frequency bands, compared to WMAPS-5, allowing it to much more effectively distinguish the true cosmic signal from contaminating foreground emissions. The glow of interstellar dust in our galaxy, radiation from synchrotron emission, and the thermal signature of hot gas in galaxy clusters. Planck stared at the sky for more than 4 years, methodically scanning the entire celestial sphere, building up the most detailed, the most precise, and the most beautiful map of the cosmic microwave background ever made. Each pixel in the final map represented a tiny patch of sky roughly 5 arcminutes across, an angular resolution 6 times sharper than Kobe, and more than twice as sharp as WMAP. Its first cosmological results released in March 2013, refined the age of the universe to 13.798 billion years. Subsequent data releases, incorporating additional calibrations and analyses, further refined this to 13.787 billion years, plus or minus 20 million years. This number, usually rounded to 13.8 billion years, is the one you will find in textbooks today. Planck also confirmed and refined WMAP measurements of cosmic composition. It found the universe to be about 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. It confirmed the flatness of the universe's geometry, and it found a few tantalizing anomalies, including a slight asymmetry between the two hemispheres of the CMB sky and a large, unexplained cold spot. Whether these anomalies are statistical flukes, artifacts of data processing, or hints of genuinely new physics remains an open question. Independent confirmation came from the Atacama Cosmology Telescope, a ground-based instrument perched at an altitude of 17,000 feet in the Atacama Desert of Chile, one of the driest and most transparent places on Earth. Using a completely different set of instruments and analysis techniques, the ACT team arrived at an age estimate consistent with Planck's, providing a crucial cross-check. 13.8 billion years. That was the answer, confirmed by multiple independent methods, using technology ranging from space-based satellites to high-altitude ground telescopes. The age of the cosmos, once the subject of mythological speculation and theological calculation, was now known to a precision that would have seemed miraculous to every astronomer who came before. But even as the community celebrated this triumph of precision cosmology, an unsettling discrepancy was emerging. Two different methods of measuring the universe's expansion rate were giving two different answers, and the gap between them, rather than closing as measurements improved, was getting wider. The universe, it seemed, was not quite done surprising us when you measure the expansion rate of the universe using the cosmic microwave background. As Planck and WMAP did, you are looking at the universe as it was 13.4 billion years ago, and using the standard model of cosmology to extrapolate forward to the present day. The number you get for the current expansion rate, the Hubble constant, is about 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.26 million light years, galaxies are receding from us at an additional 67.4 kilometers per second. But there is another way to measure the Hubble constant. Instead of looking backward from the infant universe, you can look at the universe as it is right now. You can measure the distances to nearby galaxies using Cepheid variables, Henrietta Leavitt's gift to science, still paying dividends a century later, and calibrate the brightness of Type 1a supernovae in those galaxies. Then you can use those supernovae to measure distances to galaxies much farther away, where the expansion of the universe dominates over local motions. This method, known as the cosmic distance ladder, has been refined over decades by teams of meticulous observers. The most prominent of these is the SH0e's team, led by Adam Rees of Johns Hopkins University, one of the co-discoverers of dark energy. Using the Hubble Space Telescope, and more recently, the James Webb Space Telescope, Rees and his colleagues have measured the Hubble constant to be about 73 kilometers per second per megaparsec, 67 versus 73. That might not sound like a large difference, barely 9%. But given the extraordinary precision of both measurements, each with error bars of only 1 or 2%, the disagreement is statistically enormous. The gap between the two values is not something that can be attributed to random noise or sloppy measurement. The statistical significance of the discrepancy has now exceeded 6 sigma, meaning there is less than 1 chance in a billion that it is a random coincidence. In the language of physics, a 5 sigma discrepancy is the threshold for claiming a discovery. The Hubble tension has blown past that mark. This is not a minor quibble between rival research groups. This is, in the measured and careful language of physicists, a crisis. It suggests that something fundamental about our understanding of the universe may be wrong. It has a name, the Hubble tension, and as of early 2026, no one knows how to resolve it. If the distance ladder measurements are correct, and the universe is expanding faster than the CMB predicts, then either the standard model of cosmology is missing something, or one of the measurements is wrong. For years, many physicists assumed that the problem lay with the distance ladder measurements, which involve a long chain of calibrations, each of which introduces potential errors. Perhaps the Cepheid measurements were contaminated by crowding, the difficulty of measuring a single star's brightness in a dense stellar field. Perhaps the supernova calibrations had hidden systematic biases, but in 2024, the James Webb Space Telescope effectively eliminated the crowding hypothesis. JWST's infrared capabilities allowed Rees's team to observe Cepheid variables with 4 times the resolution of the Hubble Space Telescope, seeing through the dust that had plagued earlier measurements and resolving individual stars far more cleanly. The result was the same: 73 kilometers per second per megaparsec. See, the discrepancy with the CMB was real, not an artifact of blurry vision. Other approaches have yielded mixed results. Wendy Friedman of the University of Chicago has used the tip of the red giant branch, or TRGB, method, an alternative distance indicator, and initially found values closer to the CMB prediction. But a June 2025 study using JWST data with TRGB calibrations reported a Hubble constant of roughly 70.4, with error bars large enough to be consistent with both the CMB value and the Cepheid-based value. Critics pointed out that the wide uncertainties reflected the limitations of calibrating against a single galaxy, NGC 4258, and that the result did not definitively resolve the tension. Meanwhile, a team led by Daniel Skolnick of Duke University used a different technique entirely. In January 2025, Skolnick and colleagues measured distances to galaxies in the Coma cluster using the fundamental plane relation for elliptical galaxies, a method completely independent of Cepheids, TRGB, or supernovae. Their result: 76.5 kilometers per second per megaparsec, even higher than the Cepheid-based measurements. At the American Astronomical Society meeting that month, Skolnick declared that the Hubble tension had escalated from a tension to a crisis. In December 2025, yet another independent measurement deepened the puzzle. The TDCO-SMO collaboration, using a technique called time delay cosmography, measured the Hubble constant by analyzing light from distant quasars that had been gravitationally lensed. Its images split and delayed by intervening galaxies. Their results aligned more closely with the local distance ladder values, clashing with the CMB prediction and further strengthening the case that the tension is real, not an artifact of any single measurement method. Even the Dark Energy Spectroscopic Instrument, or DESI, has added a new wrinkle. DESI has been mapping the three-dimensional positions of millions of galaxies to trace the expansion history of the universe. Its results, released in stages during 2024 and 2025, have hinted that dark energy might not be the simple cosmological constant that the standard model assumes. Instead, the density of dark energy may be evolving over time, getting stronger or weaker as the universe ages. If confirmed, this would represent a fundamental revision of our understanding of the cosmos. But intriguingly, DESI's analysis shows that allowing dark energy to vary actually makes the Hubble tension worse, not better. The expanding universe is more complicated than anyone imagined. So, what could explain the discrepancy? The proposed solutions are varied and speculative. Some theorists have suggested the existence of early dark energy, a burst of accelerated expansion in the first few 100,000 years after the Big Bang that would have changed the acoustic oscillations in the CMB, altering the inferred expansion rate. Others have proposed additional species of neutrinos or other light particles, dubbed dark radiation, that would have increased the expansion rate in the early universe. Still, others have considered more radical possibilities, modifications to the theory of gravity itself, interactions between dark matter and dark energy, or even the idea that we live in a region of the universe with slightly lower than average density, a cosmic void that would make our local measurements systematically different from the cosmic average. None of these proposals is universally accepted. Each solves one problem while creating others. The early dark energy model, for instance, fits the Hubble tension data, but is in some tension with measurements of the growth of cosmic structure. The dark radiation model helps with the expansion rate, but requires particles that have not been detected in any laboratory experiment. And so the community waits for more data. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is currently mapping the shapes and distributions of billions of galaxies to create the largest and most detailed three-dimensional map of the universe ever constructed. Its major data releases, expected around 2026, should provide powerful new constraints on dark energy and the expansion history of the cosmos. NASA's Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will survey the sky with a field of view 100 times larger than Hubble's, providing an enormous data set for studying supernovae, Cepheids, and the large-scale structure of the universe. The Hubble tension may turn out to be the crack in the cosmic edifice through which genuinely new physics pours in. Or it may ultimately be resolved by some subtle, prosaic systematic error that nobody has yet identified. Either way, it is a vivid reminder that the universe has not finished revealing its secrets, and that even our most precise measurements are approximations of a reality that is stranger and more complex than we can yet comprehend. 13.8 billion years. That is the current best answer to the question that has haunted our species since the first hominid looked up at the night sky and wondered. It is a number refined over centuries of effort, from Usher's 6,000 years, through Kelvin's 20 million, past Hubble's initial 2 billion, through the careful recalibrations of Baud and Sandage, to the exquisite measurements of Kobe, WMAP, and Planck. Consider what that number means. Try to wrap your mind around it. It is a span of time so vast that the human brain evolved to deal with seasons and lifetimes, and the migration patterns of herds simply cannot process it in any intuitive way. Carl Sagan, in his landmark 1980 television series Cosmos, found a way to make the timescale graspable. He compressed the entire history of the universe into a single calendar year, a cosmic calendar in which the Big Bang occurs at midnight on January 1st, and the present moment falls at midnight on December 31st. In this framework, each month represents a little over 1 billion years. Each day represents roughly 40 million years. Each second encompasses about 438 years of real time. On this calendar, the Milky Way galaxy does not form until sometime in March. Our sun and its planets do not coalesce from a cloud of gas and dust until early September. The first simple life on Earth, single-celled organisms, appears around September 21st. But complex multicellular life does not emerge until mid-November. Dinosaurs walk the Earth during the final week of December, appearing on December 25th, a fitting Christmas present from evolution, and going extinct on December 30th. The first members of our own genus, Homo, appear on December 31st at roughly 10:30 in the evening. All of recorded human history, every empire that rose and fell, every war fought, every poem written, every symphony composed, every scientific discovery made, from the cave paintings of Lascaux to the launch of the Planck satellite, occupies the final 14 seconds of December 31st. The entirety of human civilization is a flicker at the end of a cosmic year. And yet, in that flicker, we figured it out. We traced the expansion of the universe back to its origin. We detected the ancient light from the first moments of cosmic transparency. We measured the chemical composition of the primordial plasma. We mapped the acoustic oscillations, the frozen sound waves of the infant cosmos. We calculated the age of everything to within a fraction of a percent. And we did all of this from the surface of one small world, using instruments built from materials that were themselves forged inside ancient stars. Because the atoms in your body were not always yours. They have a history far older and far stranger than any human story. The calcium in your bones was created in the heart of a massive star, fused from lighter elements at temperatures of billions of degrees, then hurled into space when that star exploded as a supernova. The iron in your blood was forged in the core of a dying stellar giant during the last seconds before collapse. The oxygen you are breathing right now was manufactured inside a star that no longer exists, a star that burned through its nuclear fuel and scattered its enriched remains across a nebula that eventually condensed to form our sun and its system of planets. The carbon in your DNA, the nitrogen in your muscles, and the phosphorus in your nerves, all of it was cooked inside the furnaces of dead stars and seeded across the galaxy by their violent deaths. You are, in the most literal and scientifically precise sense, the universe examining itself, a collection of 13.8 billion-year-old atoms that has briefly organized itself into a form capable of pondering its own origins. That is not poetry. That is astrophysics, and it may be the most beautiful fact that science has ever uncovered. The journey from Bishop Ussher's 6,000 years to Planck's 13.8 billion is more than a story of improving measurements. It is a story about the expansion of human imagination itself. Each step along the way required letting go of a comfortable, familiar, human-scaled cosmos and accepting something vastly larger, vastly older, and vastly stranger than anything our ancestors could have dreamed. Copernicus displaced us from the center of the solar system. Darwin displaced us from the center of the biological world. Hubble and Lemaitre displaced us from the center of a static, eternal cosmos and revealed a universe that was born in fire, that is evolving, and that is accelerating into an uncertain future. And each of these displacements, painful as they may have been to the ego, opened up new realms of wonder far richer than the certainties they replaced. The universe does not care that we have measured its age. It does not notice our telescopes or our theories or our arguments. It simply is expanding and cooling and complexifying, following the laws of physics with indifferent elegance. But we notice it. We are the part of the universe that notices itself. And that is not a small thing. And still, mysteries remain. We do not know what dark matter is, this invisible substance that outweighs all the visible matter in the cosmos by a factor of 5, but has never been directly detected in any laboratory. We do not know what dark energy is, the dominant component of the universe that is accelerating its expansion, and whose fundamental nature remains one of the deepest puzzles in all of physics. We do not know why the expansion rate measured locally disagrees with the expansion rate inferred from the infant universe. We do not know what, if anything, came before the Big Bang, or whether the question even makes sense within the framework of our current physics. We do not know whether our universe is the only one or merely one bubble in an infinite foam of universes, each with its own laws of physics. We do not have a complete theory of quantum gravity, the long-sought framework that would unify Einstein's general relativity with quantum mechanics and perhaps illuminate the very first instant of creation, the moment when the entire observable universe was compressed into a volume smaller than a single atom. These are not failures. They are invitations. They are the open doors through which the next generation of scientists will walk. Somewhere, right now, a student is staring at a textbook or a computer screen or a data plot from JWST and feeling the same pull of curiosity that drew Henrietta Leavitt to her photographic plates in the early dawn of the 20th century. Somewhere, a young physicist is grappling with the Hubble tension, turning the numbers over in their mind, wondering if the answer might lie in early dark energy or modified gravity, or something nobody has yet imagined. Somewhere, a child is looking up at the night sky for the first time and asking the same question that our ancestors asked around their campfires 100,000 years ago. What is all of this, and how long has it been here? The universe took 13.8 billion years to produce a species capable of asking that question. It took that species roughly 10,000 years of civilization to answer it. The answer came not from any single genius, though there were many geniuses along the way. It came from the collective effort of thousands of people across dozens of countries and hundreds of years. Priests and poets, farmers' daughters and Nobel laureates, kayakers and mule drivers, pigeon wranglers and satellite engineers. 13.8 billion years of cosmic history, roughly 300,000 years of modern human existence, a few centuries of science, a handful of decades of precision cosmology, and still so much left to discover. The universe is ancient. It is expanding. It is accelerating. It is full of dark substances we cannot see and dark forces we do not understand. its age is known to within a fraction of a percent. And yet the meaning of that age, the full story of how 13.8 billion years of physics and chemistry and gravity and starlight conspired to produce a world in which conscious beings ponder their own origins, remains as mysterious and as beautiful as ever. We are only just getting started. If you enjoyed this exploration of the age of the cosmos, please like and subscribe, and leave a comment to tell us what questions about the universe you would like us to explore next. Thanks for watching, and we will see you next time.